Okay, so here's what happened in previous semesters. My test 3 ended at chapter 8. So I end my test 3 with central limit theorem plus Bayes theorem. Central limit theorem plus Bayes theorem. Okay, now recently in the last 3 semesters, I think maybe 3 semesters, maybe 1 year, including winter or summer, I don't remember precisely. Okay, I included 9.2 in my test 3, and that 9.2, the one that if I include it, it's the one with confidence interval for mu with sigma known. Happens to be the one not in your textbook. Okay, but starting from this summer, I will include chapter 9. Okay, I will include chapter 9. I just get that a new note coming in. So this test 3 will include chapter 9, 9.1, 9.2, 9.3, which in the past was part of my test 4. So if you study, I expect you to study for your test 3 during this weekend. Okay, and I tell you this so that you actually do some digging into my old test 4. Okay, in my old test 4, in my previous test 4, I have most chapter 9 and chapter 10, some chapter 11. Now, my plan for this test 4, our class, okay, test 3 up to chapter 9, and your test 4 will be full chapter 10, chapter 11, and linear regression. Okay, that's my plan for this. Because of this, in the past, I did not include linear regression in my test 4, and the only time students saw linear regression problem was in the department final or in the final. And at WLAC College, some instructors take it very, very seriously about having linear regression being part of the curriculum, while in our syllabus, not only my syllabus, but also the syllabus, the curriculum for WLAC College, linear regression is supposed to be just one of the optional topic of 2 topics that I'm supposed to cover. Okay, so instead of being optional of 2, so I can choose which 2 topics I want to cover, linear regression turns out to be something big that takes approximately 20 points in the department final. And instead of telling them to adjust, I would like my student to actually learn more. I think that's the correct one. Instead of we lower down the quality, we increase for adjustment instead. Okay, now I hope you understand this adjustment. So you see that I actually slowly move my classes not to be too significant change from one semester to the next semester. You know, okay, but yeah, but I think that's a necessary change to do. Okay, now let me go on to this 9.3. 9.3 is confidence interval for population variance, and consequently, we can go on later on to confidence interval for population standard deviation. Okay. Now, this model, so the way we construct confidence interval for sigma squared here is not taught in a lot, not only a few, not only some, but a lot of universities. Because of the strict requirement. Because of the strict requirements needed, and that is that the underlying population from which we select the sample, needs to be normally distributed. Okay, and this model does not rely on central limit theorem. At least it's more than just central limit theorem. Now, central limit theorem, just to remind us, central limit theorem, for us to apply central limit theorem, there's two requirements. Either the underlying population is normal or approximately normal. It doesn't have to be strictly normal, or just approximately normal is good enough. And by increasing the sample size, then it becomes normal, right? As long as it is symmetric, bell-shaped, then with sample size of 10 or 20, it's already normal. Or another way is that the sample size is at least 30. Okay, that's for central limit theorem. The thing with this model that we do here, that the underlying population needs to be strictly normal. Now, to make it even worse is this. The distribution of sample variance is not robust. What is that, Thomas? It's not robust in this sense that even if we increase the sample size, the sample variance may move even further from the actual population variance. Now, basically, it's like this. Remember central limit theorem? For central limit theorem, it's robust in the sense that if we increase the sample size, okay, then the sample mean, not sample variance, the sample mean will move even closer to the actual population mean. Basically, if we increase the sample size, then the variance of sample means will be smaller. So X bar will get closer to mu as we increase the sample size, because the variance of sampling distribution is the original variance, the variance of the original distribution divided by square root of n. So the larger the n, the smaller the quotient b. Okay, that's for central limit theorem. Now, what happened now is the following. Now, if the x deviate just a little bit, from normality, from normal distribution, then what happened is then the sample variance will not go to population variance even if we increase the sample size. Okay, as long as it is sample and you have some material that you don't pick it, you don't include in the sample, there is a chance, not always, but there's a chance that the sample variance is actually getting further away from the actual population variance. Okay, that's what we mean by not robust, means increasing the sample size may make the situation worse. Okay, may make the situation worse. If the underlying population is not normal or just a little bit off from normal. So the requirement is very strict. We need this to be normal. Okay, we need this to be normal. Maybe to say further, the variance of the sample variance distribution. It's kind of hard to say. Yeah, may explode to infinity. The variance. So if you let's say you have X, right, and then you do sample of, let's say you do sample of 2. Okay, so you have X1 and X2. Now, then you look at the variance. So let's say you have this. I think I remember the last example we have was like 5. Is it? Or no, 3, and then 7, and then 11. Okay, and then you do this sample. All possible samples are 3, 3, 3, 7, 3, 11, and then 7, 3, so on and so forth. Now, then you find the variance here, variance here, variance here, variance here, variance here. And then from each variance, okay, you find the variance of those variances. Now, you will see that the result may not be the variance of the original underlying distribution or in any way related to it. No, it's not. Okay, that's why I don't even want to show you. That's why I don't even want to bother to show you. Now, because of the very strict requirement and the resulting interval that we get is actually way too big, that it's almost to the point that it's useless for us to do this modeling, and therefore a lot of universities not even teaching this. Okay, now, so Thomas, why do you teach this? Oh, by the way, this section is supposed to be part of our curriculum, but then I was told that they will remove this from department final, so there will be no problems from this section in the department final. But that was said by the person who wrote the department final last semester. Okay, so the person who write the department final this summer, okay, may not have the same idea. So just to make sure that if they ask that question, we still can handle this, then I teach you. Okay, now I spend approximately how many 20 minutes just to explain the background of this. Okay, that the model will be as the following template. Do I template like this? Template like with A, huh? Okay, the template. Okay, there is no best point estimate. There is no best point estimate. Okay, we may some textbook, I think including our textbook, say there's a point estimate later on, but there's not a best point estimate. Okay, not best. I need to de-emphasize the word best here. Okay, now because there is no best point estimate, then the structure will not be the sample variance and then you add or subtract margin of error. No, it will not be in this style anymore. No, it's not like that anymore. It's not like what we had before is that to estimate mu, so we use x bar and then we plus margin of error minus the margin of error, right? Okay, or p hat plus margin of error minus margin of error. Okay, that's because we have best point estimate. Okay, but right now we don't have best point estimate, therefore it will not be that style. Okay, it will not be that style. It will not be best point estimate plus margin of error minus margin of error. Now, instead, we will have this. We'll have this. Step 1, we will do chi-squared right. Step 2, chi-squared left. Oops. And you can do this interchangeably. You can do 1 and then 2. Okay, either 1 first. Okay, and then your step 3 will be just like before. You need to have declaration first. The confidence interval for sigma squared, and then once we get that confidence interval, if we need the confidence interval for population standard deviation, we apply square root to each side. Now, confidence interval for for sigma squared is n minus 1 times sample variance over chi-squared right less than sigma squared less than n minus 1 s squared, the degree of freedom times sample variance over chi-squared left. Now, later on, for the confidence interval for population standard deviation, you apply square root to each one of those. Because if you apply square root to sigma squared, you will get sigma, which is population standard deviation. Okay, now so the issue we have here then is this: how to get this? How to get this? Because once we get this, then we get the denominators here. You see chi-squared, right? Okay, in the formula will be on the denominator of the left-hand side, and chi-squared left will be on the right-hand side, the denominator of the right-hand side of that inequality. Okay. Now, chi-squared distribution is a non-negative distribution. Chi-squared distribution is a first non-negative distribution. Just imagine that the variance you get can never be negative, right? The variance, whatever the distribution, whatever this the underlying population distribution for the variance, the population, okay, the variance will never be negative. That's why then when they create chi-square distribution, they use that square notation to emphasize that it is non-negative. Okay, it's non-negative distribution. And second, it's non-symmetric. In fact, it's skewed to the right. It is skewed to the right. Okay, it looks like this. It looks like this. So let me use red color for the distribution. It looks like this. Okay, it looks like that. And even when we get the peak, that's not the mean. That's not the mean. In other words, the area to the left, yeah, as I know, it's not the mean. The area to the left of this peak here and the area to the right of that peak are not 50%. I'm not sure, but I think it's not. Okay, and the peak here is, as I know, that's the degree of freedom. As I know, that's the degree of freedom, or n. I don't remember which one. Okay, but it's not important. It's not important. It's either one of them. It's either one of them. Okay. Now then, what is chi-squared right? Chi-squared right is the following. Chi-squared right is the following. So let me draw it even bigger now. Let's say this is our chi-squared distribution. Okay. Now, they will tell us the confidence level, right? Confidence level will be the area in the middle such that the area of the tail are equally shared. Like let's say for example, just for example, the confidence level is 95%. So the remaining 5% is being shared by these two tails. This is 2.5%. This is 2.5%. Okay. Now the thing is, it is not symmetric. Okay. And the one called chi-squared right is the one on the right-hand side. Okay, and chi-squared left is the one on the left-hand side. Okay. Now, let's learn to find this critical value first. Let's learn to find this critical value first. So, little examples. Let's say part A, we have a sample size, let's say 20. Okay, the sample size is 20. And then confidence level is 95%. Okay, now the way the program being done with the one I asked you to program with your calculator, okay, the way it is being done is that the area will be area to the right. So later on, this is 95% in the middle, okay, and then this is chi-squared right. Okay, now then our chi-square right will be inverse chi-squared. Maybe I don't remember what notation they use. Inverse chi-squared. That's just notation. I think inverse chi. I don't remember what notation we use for that program. Let me look at my calculator. I forget myself. Inverse chi. Now then, the first number will be the area to the right. The first number will be the area to the right. And then the second number will be the degree of freedom. Okay, so in this case, in this case, the area to the right will be, let me erase the area to the right will be 0.025. That's the area to the right. To the right of that critical value. And then the degree of freedom is, the degree of freedom is 19. Okay, so chi-squared right is inverse chi 0.025 and the degree of freedom is 19. Okay, can you do that by the way? Using the calculator that I assume you already programmed. Yeah, it may take a while though. It may take a while. It may take a while. It may take a while. So let me see if I use mine. I have not programmed the one on my calculator, my computer calculator. Not yet. Let me see. Somebody tell me something. Let me wait. Chi-squared 5. I'm still waiting for the calculator. Yeah, it's 32.85233. That's right. That's this gives me 32.85233. Now chi-squared left is the critical number such that the area to the right again, it's 95 plus that one tail. Okay, that's inverse chi 0.975. Okay, you do that, I do that too. Now, the thing is, if you have not programmed your calculator, please take a look on that YouTube video clip, that YouTube video that I quote. Okay, and then program that. You definitely need this for your test 3. Okay, you definitely need this for your test 3. Okay, so suppose I continue from here. Suppose then we know that the sample variance, let's say, is 10. I just make up numbers. Okay, let's say sample variance is 10. Then what happened with my step 3? My step 3, of course, we start with declaration. 95% confidence interval for sigma squared is given by degree of freedom 19. Yeah, let me keep 19 times 10 over chi squared right 32.85233 less than sigma squared less than 19 times 10 over 8.9065 0.52. Okay, now whatever the number you get, let me just use my calculator. 190 divided by 32.85223. So I get 5.7834 less than sigma squared less than 190 divided by 8.90652. Okay, 21.33269. Now then, when I do the confidence interval for population standard deviation, then I go on, always do the declaration first before you even start the formula. Okay, and that will be the square root of this guy square root of this guy. This is 4.61873. This will be 2 point something. Square root of 2.40488. Okay, so what are important here? You need to know how to find the critical value. Okay, even though there are two steps, it's actually one same thing being applied. Just be careful which one is the right chi-squared right, which one is the chi-squared left, and then the next thing you need to know is the formula. Okay, now, but be careful with one thing. What I use here is S squared. That's why I just put 10 there. That's the position for sample variance. However, you know our textbook usually, instead of giving sample variance, our textbook usually gives sample standard deviation instead. Okay, if the one you get is sample standard deviation, don't forget to square it. Okay, don't forget to square it. Again, because the formula is n-1 times S squared over chi-squared right less than sigma squared less than n-1 S squared over chi-squared left. Okay, so what I want to emphasize is the position here. On the numerator, it's not sample standard deviation. No, it's sample variance. While the information given to you in the test may be sample standard deviation. So you need to do that little adjustment. Okay, now I think we are ready with a problem from our textbook. Let me open our textbook. Set. You know what? I'll just do one problem right away. I'll just do one problem right away. Suppose for example, the sample size, let's say, is 10, and then the sample standard deviation is, let's say, 4.7, and then we want to construct a confidence level of, let's say, 92%. Now, in the past, even though I asked this kind of question to my students, most of the time they use table. They didn't use calculator. Most of the time they didn't use calculator. Even after we start using TI-84, the first semester, the first 2 semesters, I didn't enforce them to use programming from calculator. Okay, so even though they use TI-83, they still use a table when it comes to chi-square distribution. In the last 2 semesters or 3 semesters is when I say that, you know what, let's just program. Okay, now, so this one here, step 1, chi-squared right will be, I think I need to say population is normal. Population is normal. Now, in the past, again, the requirement that the population is normal may be substituted by a sample size greater than 30. Right now, no. Even if your sample size here is 100, you still need to have a population is normal. Okay, otherwise the model that we get later on will not be that accurate anymore. It looks like this, the chi-square distribution. Okay, now then we need 92% in the middle, 92% in the middle, such that the area of each tail is 8% divided by 2, it's 4% here, and it's 4% here. Okay, so this is chi squared right, this is chi squared left. So what is the notation for chi squared right? It will be inverse chi, area to the right, 4%, degree of freedom is 9. Chi squared left, the area to the right is 96%, degree of freedom is 9. Use your calculator. Inverse chi, area to the right, 0.04, degree of freedom 9. It takes a while. I get 17.60828, and then for inverse chi, 0.96, area to the right, and then the degree of freedom is 9. This will be 3.1047. Now you will see chi-square right has to be more than the sample size. This number here, chi-square right, has to be greater than sample size. Remember I said that the peak is either degree of freedom or the sample size, I don't remember precisely. Okay, now chi-square right should be more than that, and chi-square left must be less than that. Okay, so chi-square left must be to the left of the sample size, and not just to the left a little bit. It's like more than 1 point. That's why I didn't remember if it's supposed to be the peak here, supposed to be the sample size or degree of freedom. I can try to find out later on, or maybe not neither one of them, but around those two numbers. Okay, and then step 3, 92% confidence interval for sigma squared will be degree of freedom 9 times sample variance 4.7 squared. I hope you know why this time I square it. Okay, because the one provided to us is sample standard deviation. Okay, now at this point, if you still cannot distinguish sample standard deviation and sample variance, something really wrong with you. Okay, you should have studied even more. Okay, and then over 17.60828 less than sigma squared less than 9 times 4.7 squared over 3.10467. 9 times 4.7 squared divided by 17.60828 is that's 11.29071 less than sigma squared less than something. But let me just go on with my calculation. So 92% confidence interval for sigma I already have that on my calculator right now. Let me apply the square root right away to get the left fence. I will get 3.36017 less than sigma less than blah. 9 times 4.7 squared divided by 3.10467. This is 64.03579, and the square root of that will be 8.00224. Okay. Now, when even I know some people just like to do the confidence interval for population standard deviation right away, and you apply square root right away here. That's actually not proper. Okay, for you to get the standard deviation, remember when you show your work, it's not only just to find the final answer. When you show the work, you make people understand. That's part of statistics, though. You like it or not. Okay, you like it or not. So there's some tradition, some procedure that you need to follow, and it's not just the final answer. Okay, not just final answer. But Thomas, I get the right answer. Yeah, but your procedure is wrong. Okay, and one way people lie is by doing something else and then come up with the result that everybody likes, right? You just tell them what makes them happy. That's not critical. No, that's not critical. I need to build, to improve, to develop students who are able to find the mistakes even in the teachers, even in me. So if you are not someone who can be detail oriented yourself, you won't be able to tell what's wrong with other people because you yourself cannot tell what's wrong with you. Okay, now by showing the details, you will be able to tell other people that you make a mistake here without being personal. Okay, without saying that, you just do it wrong. What's wrong? You just do it wrong. I don't know how to show you. What kind of answer is that? Okay, remember when we were teenage, some of you still teenage, and then our parents tell us, no, you cannot do that. Why? Just don't do it. Do you like that answer? Now, of course I do that to my son because he's not mature yet. But even though he's not mature yet, I don't want him to play, for example, with knife, right? Okay, why? He does not need to understand how dangerous is knife for me to tell him not to use it. But we are adult here. Now telling you not to do one thing or to do another thing without giving you the reason, okay, is basically treat you as immature. Okay, and if you do that to me, of course, I can say I get offended. Okay, yeah. Okay. Now, of course, there are things in statistics I have to say it is done this way. Why it is done this way? Because the previous people did it this way. Okay, that's the worst answer I can give, but at least that's what other people did. Okay, and one of them is when you need to construct confidence interval for population standard deviation, you need to do this first. Okay, you need to do this first. You need to do this first. Then you do this one. Okay. Now, let's do a problem from the book. That will be word problems, of course, once it is from the book. Let's see. That will be 9.3. Oops. Oh yeah, I did 9.3. That will be 9.3. A second. There's a chance I only do one problem from this. Let's go ahead with number 12 right away. 9.3 number 4. Okay, travelers pay taxes for flying, rental cars, and hotels. The following data represent the total travel tax for a 3-day business trip in 8 randomly selected cities. Now, note that Chicago has the highest travel taxes in the country at 101.27. Now, in problem 32, it was verified that the data are normally distributed. Okay, so they verify that using test for normality, which we will not do. Okay, but the important one is that the sample standard deviation is $12.324. So what we need from here is the sample size is 8. The sample standard deviation is 12.324. The confidence level is 90%. Now, I would like you to, of course, suppose we don't have this, what do you do? Suppose they don't give this to us. Then what you will do is you will need to compute the sample standard deviation from here. Okay? If I ask you to do it manually, then you need to find, if I ask you to do it manually, then you need to find the n. Of course, that's easy, that's 8. You need to find the sum of x, the sum of x squared, right? And then from there, you compute the s squared. Therefore, you find the s. If you do it manually, okay? Now, if I say that just find it using your calculator, then you plug this into your calculator. Let me remind you where to plug that in, into the list, So you can confirm that using your calculator. In a second, I'm calling my calculator. Okay, so you can use your calculator and then you go to stat, edit. Let's say you use list tool right now. Okay, so you plug in numbers. Okay, but this is what you do if you just want to confirm if you did it right, or if I tell you just use your calculator to find this result. So you still need to know how to use calculator though. Your department final, assume you know how to do this. Okay, so when they ask you this kind of question in my test, it's supposed to be like at least 5 minutes question, but in your department final, they assume this is supposed to be only 1 or even 2-minute question. The last one is 90.29, enter. Then if I want to find the sample standard deviation, I go to calculate one variable statistic. And we were using L2. Second, L2 here. This is L2. This is L2. I hope you see that. Okay. I can ignore the frequency list. So you see the sample standard deviation is 12.32363. You know what? Let me do this. Okay. Now then what I want to do, I'm about to give you a break. I want to continue with this. Just construct the 90% confidence interval for standard deviation. So you do your step 1, your step 2, and step 3, the first part and second part. That should take you 1, 2, 3, 4, 5 minutes together with your break. We come back at, let's say, 9:18. We come back at 9:18. But 9:18, we are done with it. So chi-squared right will be inverse chi 90%. So the area to the right is 0.05. Degree freedom is 7. And then I need to wait. While waiting, let me just write chi-squared left will be inverse chi 0.95. That's the area to the right of the critical value we're looking for. And degree freedom is 7. While waiting, let me write 90% confidence interval for sigma squared. This is 2.16735. So this one is degree freedom 7 times sample variance 12.324 squared over chi-squared right 14.06714 less than sigma squared less than 7 times 12.324 squared over 2.16735. Here I get 75 point something. 75.57804 less than sigma squared less than let me just continue with my calculator. I will apply square root to the last number I have. I get 8.69356 less than sigma less than 7 times 12.324 squared over 2.16735. It's 490. So you see the variance actually very big difference. And then applying square root from there, get 0.2 and 809. Okay. Give me a second. Okay, now let me see for suggested homework. Where did I put it? Did I? Your suggested homework from this section will be 9.3. Number 11 to number I think number 11 to number 9 to number 15 is good enough. Number 9 to number 15. Suggested homework will be on this 9.3, number 9 to number 15. Will be odd ones. Okay, that's good enough. Okay, I usually ask only one problem from here in my test though. I usually ask only one problem from here in the test. By the way, let me create a little poll. Let me create a little poll. I want to create a poll, but edit. Let's see. I wonder if do you want a quiz? Of course, the one that you do at home and then you turn it in later, right? Not in class quiz. Before next test, and if so, when is the due date? Let me share you my screen. Do you want a quiz? And if so, when would the due date be? Okay, multiple choice. So the first answer is no, the second answer is Monday, the third answer is Tuesday, and the last answer is Wednesday. Do you want Thursday? Oh, just put it in. See? I wonder how. Oh, no, I want to make it anonymous. The thing is, I wonder if I can. I get somebody give me answer already, but I need you to do the poll. But the thing is, like, I wonder how to launch the poll. No, not this one, not this one. And poll. Oh, sorry. It's this one. Okay, launch poll. Okay. Only 9 of you will vote for this. Okay, do you see the poll? Okay, tell me what you want. It seems like Tuesday wins, huh? Okay, but this also means that of 9 people actually attending this, it's actually there's supposed to be 9 participants, right? Okay, only 7 actually pay attention. Ah, now you tell me. Good thing I make it anonymous so that I don't know who. Okay, but this is 6-1 for Tuesday. So even if the other 2 people coming in say no, the answer is still Tuesday. Sorry. Boom. Okay, so yes, we will have a quiz that due on Tuesday. I actually don't like to give you any homework or like that quiz, but I give it to you so that you have a feeling of what your test will be. Okay, yeah, and that also makes you study earlier. Okay, I actually prefer you to turn it in on Monday, such that I have more time to actually grade it and then give it back to you before Thursday. Now, but if you give it to me on Tuesday, then I have basically only 1 day to grade it. I have to give it back to you on Wednesday, basically. Okay, but you know, it's actually up to me, right? So when will we get the quiz solution to help us study for the quick test? Good. My plan is this. The due time will be Tuesday around 8:06, right? Tuesday on 8:06. So after that Tuesday, let's say after the lecture on Tuesday, then I will post the solution. Okay. So even though I don't give the result, your quiz back to you, the graded quiz back to you, at least you have the solution to study from. Okay. I hope that's good enough. Okay. Now let's go back to our class. I think the sharing, I need to change the sharing. Go back to our class. Now the next section we will do is a very big section. It's a very big section. So instead of calling that 10.1 or 10.2, 10.3, I will call that chapter 10 introduction to hypothesis testing. Introduction to hypothesis testing. And I will insert a file that I did last semester. Actually, I don't think it's last semester. I did it in the winter. Give me a sec. I wonder if this will do. Okay. Okay. Hypothesis testing consists of 6 steps. Okay. Consists of 6 steps. And when you do hypothesis testing later on in my class, you need to do these 6 steps. In fact, you still even need to write one claim, two statistical hypothesis, so on and so forth. Okay, there will be 6 steps that we will go over in this hypothesis testing procedure. With the time I have left around 30 minutes, I think I can only go as far as step 1, 2, 3. Now I will leave this note here so that you can start reading for during the weekend, and I may even give the next handout, the continuation of for this handout here. Okay, now the first step about the claim. Now the claim is a statement that has exactly one truth value, either true or false. Now, in this chapter, we will only deal with claims about parameters on population mean, or population mean with sigma unknown, or population proportion, or population variance, population standard deviation. Now, a claim may be explicitly provided in the problem, okay? Otherwise, if they don't explicitly say that, then you need to paraphrase that becomes a claim. Now, to be more precise, let me give you more examples about a claim. A claim is, for example, the mean of the overall mean of West LA College students GPA is at least 3.0. Okay, the thing is, it is a statement. Okay, it is a sentence that can be true or can be false, but cannot be both, cannot be neither. Okay, so either this statement is true or false. Now, one sample statement, but not the one we will be dealing with, is the following statement. Suppose I say today is Friday. Now, this statement is either wrong or false. It cannot be, I don't know. Okay, no, cannot be. Well, it depends on, you know, it can be both. No. Today is Friday is either true or false. Okay, of course, today is Thursday, so this statement is false today. Okay, now the following is not a statement. The following is not a statement. How are you doing? That's a question, that's not a statement. Even though I understand some question implicitly carry some statement. If somebody asks you, how are you doing? And of course, at least that person care, right? Okay, but this statement, this sentence itself is not a statement, it is a question. Okay, so there's no truth statement is that, in that. Now, the answer of this question is the statement. How are you doing? I'm doing well. That's a statement. Okay, now that's the statement that can be wrong, can be true, can be false, right? Okay, yeah, but the one we are dealing with in this chapter is only the claims about the parameters. So in this case, in these small examples I gave you here, that's the claim about the population mean. Okay, that's the claim about the population mean. Now that's one, it's about the claim. I think the claim is actually quite easy until we look deeper into problems that that we need to paraphrase the claim. Okay, but most of the time the claim will be explicit. Okay, of course there are some complication later on, but I'm not teaching you the complication on the first day. On the first day you deal with hypothesis testing. No, we'll deal with easy one. Okay, usually the claim may be basically cut and paste from the sentence, test the claim that da 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 da. Okay, yeah, test the claim that the mean, the overall mean of West Island College students GPA is at least 3.00. Okay, now the thing is, this statement, this claim is in words, such that when you write your step 1 later on, it has to be in words also. Okay, basically something looks like this. Okay, basically something looks like that. Okay, step 2, statistical hypothesis. This one we get into some complication. Statistical hypothesis, or simply hypothesis, is derived from the claim that we have in step 1. Okay, statistical hypothesis is derived from the claim. We will develop two competing complementary hypotheses denoted by H0 and H1. H0 is red null hypothesis, also called original hypothesis. Status quo is the hypothesis that contains equal sign. While the alternate hypothesis, denoted by H subscript 1, is also called challenging hypothesis, the hypothesis that is complement of the null hypothesis, and therefore not containing equal sign. Okay, of course we will have example later on. We'll have example later on. Okay, but let's just do a little example right now. Let's just do a little example right now. Suppose from our claim, step 1, the claim is this. One claim is this. Now then, step 2, when we do the hypothesis, we will have two competing hypotheses. Okay, we'll have two competing hypotheses, null hypothesis and alternate hypothesis. Okay, now that's about mu, right? That's about mu. That's about mu. And if we read that and translate that claim, that claim basically say that mu is at least 3.0. Okay, now then this claim will give us two competing hypotheses. Either mu is greater or equals to 3.0, or the complement is mu less than 3.0. Okay, but the claim is here. The claim is here. This is the claim. This is the claim. Okay, that's the claim. Now, from that claim, because it can be true or false, but not both, not neither, then either one of these two hypotheses will be true. Either it's greater or equals to 3.00 or strictly less than 3.00. There are two of them. Okay, now then, once we have two competing hypotheses, then one of them will go to null hypothesis and the other one then will go to the alternate hypothesis. How do we know which goes to null hypothesis, which goes to alternate hypothesis? The answer is look at the equal sign. If it has equal sign, then that hypothesis goes to the null hypothesis, while if it doesn't have equal sign, it will go to the alternate hypothesis. Okay. Now, I am not saying that the claim will always go to null hypothesis. No, that's not right. The claim may go to null hypothesis, like in this case. It may also go to the alternate hypothesis in other examples. Okay. Now, so the notes, this is where it becomes crucial. Instead of you keep on asking me the same question, I write it down so that if anybody asks me that question again, I will say, look at the notes. Okay, look at the notes. The note says that part A, the claim from step 1 may become null hypothesis, may becomes alternate hypothesis. Now, we know the claim becomes alternate hypothesis if the claim does not imply the parameter it contains equality. So this is the claim, right? If the claim does not imply parameter contains equality, then it goes to the alternate hypothesis. Now, if the claim implies the parameter contains equality, like the example I just gave you on the right-hand side, mu at least means including, right? Contains equality, then the claim becomes the null hypothesis. Okay, that's for how do we know which goes to null and which goes to alternate hypothesis. Now, of course, you need to first, from that claim, develop these two competing hypotheses. Okay. Then from there, you decide the one with equal sign goes to null hypothesis. The one without equal sign will go to alternate hypothesis. And you will see in my class, these two signs here will be complementary. Okay, these two signs will be complementary. So you will see that if the null hypothesis use equal sign, the alternate hypothesis will use not equal. If the null hypothesis use less than equal to, then the alternate will use strictly greater than. If the null hypothesis use greater equals to, then the alternate hypothesis will be less than. Okay, at least that's what will happen in my class. Okay, now part B. In recent textbook, including our textbook, recent textbook, including ours, always use equal sign for null hypothesis. Okay. Now I said earlier, I said earlier that the null hypothesis may be one of these three signs here, right? Maybe one of those three signs there. Okay, it refers to this. Now, recent textbook, including our textbook, they changed the null hypothesis from either one of these three signs becomes only equal sign. Okay, so our textbook used that style. Now, why then our textbook being different? Not only our textbook, actually, most textbook, if not all, recently use equal sign for the null hypothesis. Okay, but the reason for this change, I will explain that in step 3. Now, I personally will use what I taught you here, that the inequality should be complementary. The inequality being used in null hypothesis and alternate hypothesis should be complementary. Okay, now, the way the hypothesis should be written, you need to have this braces here. You need to have that braces, then null hypothesis, colon, alternate hypothesis, colon. That's how it is being written. Okay, Thomas, that's not how I learned it in my previous, when I took this class first time. Okay, if you want to use your previous professor's method, why didn't you pass it first time? To be honest with you, when I grade your tests and your last quiz, I get pissed off with some people's work. Am I recording this? Yes, I am. Good. Okay, I get pissed off with some people's work because it's clearly this person didn't study from my lecture. And it's clear these students actually took this class before, but didn't study it right, but still follow that teacher's method. Okay, remember, if you are repeating this class, it's either your fault or your previous teacher's fault. It's not my fault. Don't use your previous method. It doesn't work. Especially you say that, oh, my previous teacher did this way, then why didn't you pass it first time? Okay, you want to try the same method and not listening to your current teacher? Okay, if the one grading your test later is that teacher, go for it. Okay, but if I'm the one grading it, do it my way. Okay, you need to have that sense of at least try to make your teacher happy. Okay, okay, not purposely doing things differently for no reason. Okay, and if you use the reason that that's how you learn it from your previous teacher, then actually that's a wrong reason because you failed that class. Okay, you may say it's different from the textbook, but the one in charge of this class is me, not your textbook. So that reason, even that reason is wrong. Okay, yeah, and if you look at the textbook, I'm teaching you, when I teach this class, remember my background, I did my PhD in probability and statistics. So the book I read is not only this textbook. And that makes me different from a lot of other stats teachers. Okay, I hope you can really feel my enragement. I get pissed off. Why? Because after reading so many textbooks, after studying so long, I tell you what you're supposed to do, and you still listen to those people who clearly don't know enough, but they're enough to teach statistics. Okay, what I bring to the table, what I present to you is not only what the textbook presents, but also the practical use of this. Okay, now what I don't want to happen is simply because you write it differently, people can tell right away you didn't do statistics well. Okay, the way you write things, once it becomes not structured, people can tell right away what kind of person you are. Okay, remember I once said that people will consider you smart, not because you do strange things and all of a sudden get the answer. No, that's not smart, that's strange. People call you smart if you can solve the problem in a way they could not imagine, but yet they can understand. That's smart. Oh, that's the way he did it. Man, that's so cool, right? Okay, so other people saw what you did and understand what you did, while that person cannot come up with that method on himself or herself. That's what we call smart. Okay, but if you do things that I don't understand, and whatever you do, I would just call that strange or magic or lie, whatever, right? But I will not ascribe the word smart to you. Okay, so please listen to me. Okay, it's not only about making me happy. No, in this case, this is the way they do it. Just do it that way. Okay, we start with braces. Okay, the top one null hypothesis, the bottom one alternate hypothesis, and then colon, not equal sign. Now then from there it is followed by parameter, inequality sign, and then constant. Now what I said earlier is that the inequality sign correspond to this. This is a pair, this is another pair, this is another pair. Okay, that's another pair. So you see in my example here, this pair is one of them, the last one. Okay, now we can guarantee that the inequalities has to be complementary to each other. Okay, now historical background. Null hypothesis and alternate hypothesis in the past denoted by H sub 0 and H sub A. Now see, when I write H sub 0, H sub O is supposed to be an H sub A, they may look quite similar, especially because they are the subscript, right? Because of that, to prevent misreading, okay, so they actually change this becomes 0 and this becomes 1. Okay, now if you read older textbook, they still use H sub 0 and H sub A. If you do so, I cannot mark you wrong. I want to, but I cannot. Okay, but the current notation being used is H sub 0, H sub 1. So Thomas, hold on. Sometimes you follow the old tradition, like your inequality sign, but sometimes you change to the current notation. So which method you actually use? The one that is better. The one that has the better reasoning behind it. So what happened, Thomas, if I use equal sign only for my null hypothesis? If I use equal sign only for my null hypothesis, I will be fine. Yeah, if you use equal sign here instead, right? If you use equal sign here instead, and then this is less than, I will be fine. You know, I don't mind with that. Okay, but usually those people who use that kind of sign will get confused in some of my questions. They are the one who usually get confused in some of my questions. Now, let me go back or fix that. So I have fixed that back to our previous inequality signs. Now, that's for the historical note. Let's do some problems. Just step 1 and step 2, just to get used to this. Just step 1 and step 2. Okay, step 1. A salesman claims that more than 1/4 of all customers buy his brand vacuum cleaner. So step 1, claim. So you need to write that one claim. The claim is more than 1/4, 1/4 of all customers buy his brand vacuum cleaner. And then step 2, hypothesis. And braces, null hypothesis, alternate hypothesis. Now, when we say more than 1/4, it's more than 1/4, right? More than 1/4. Now, more than 1/4 of all customers refers to the P or mu or sigma squared or sigma. Only 4 choices. P, mu, sigma squared or sigma. Now, but 1/4 of all customers refers to proportion, right? Okay, so proportion of all customers by his brand is more than 1/4. Okay, that's the claim though. Now, the thing is, this is without equal sign. This is without equal sign. Because it is without equal sign, it will go to the alternate hypothesis. Okay, so the claim may go to alternate hypothesis. The claim may go to original hypothesis, null hypothesis. Okay, now how about the null hypothesis? Then the null hypothesis must have the same parameter and the same constant, but opposite inequality sign. Okay, that's how the answer is supposed to be. However, if you follow textbook, and when I say textbook here refers not only to our textbook, but a more recent graduates instructors or those old instructors who follow the new textbook, then their null hypothesis will be written P equals to 1/4. Okay, so they not restricting the fact that null hypothesis and alternate hypothesis should be competing, should be complementary. They don't require that. Okay, we will see in step 3. I think I don't have time for step 3 today, but we will see in step 3 later on that why our textbook, just like other textbook, have this, they loosen that requirement. Okay, it has something to do with step 3. Now, question B. Test the claim that the mean body temperature of adult humans is not 98.6 degrees. So step 1, claim. So it's quite explicit, right? Test the claim that. Okay, what is the claim? The claim is the mean body temperature, the mean body temperature of adult human is not 98.6 degrees. I should use Fahrenheit there. Okay, then hypothesis. Braces, null hypothesis, alternate hypothesis, colon. From the claim, we see that the mean body temperature, that's about mu, is not 98.6 degree Fahrenheit. So I put it in the alternate hypothesis, right? Because alternate hypothesis does not have equal sign. Okay, actually to be more precise, we will put this to be more precise. Okay, now then the null hypothesis will be the complement, mu equals to 98.6 degree Fahrenheit. Okay, that's for question B. I hope you start feeling, getting used to it. So yeah, these 6 steps is actually a lot of things put together, but that's why you need to get used to it. The way I explain it will be that like in this case, I explain step 1 and step 2. I give you examples. Later on, after I explain step 3, then we do examples again. After we do step 4, we do examples again. But the example will be step 1, 2, 3, 4, like that. Okay, so the more we learn, the more step we will do in each question. Part C, claim. A serial company claims that the standard deviation, oh, this is straightforward. Standard deviation of the serial in each boxes is less than 0.5 ounces, 0.5 ounce. So step 2, the hypothesis. Null hypothesis, alternate hypothesis. Let me just go ahead. Standard deviation is less than 0.5 ounce. Okay, so the original hypothesis, the one, the complement of that, greater or equals to 0.5 ounce. I hope you start feeling how easy it is for step 1 and step 2. Okay, so I don't expect people to make mistake in step 1, step 2. I still saw it though, but most of the time, if it happens, and that student actually is well prepared, it's simply misunderstanding of the problem. Okay, let's go on to more questions, but this time we have more realistic. The question ABC that I did earlier is actually part of the paragraph, but that sentence, each of these question sentence from those questions go directly to the claim. Now, the actual problem may be longer, like question 1. The NAEP is administered annually to 4th, 8th, and 12th graders in the United States. On the math assessment, a score above 275 is considered an indication that the student has the skills to balance a checkbook. Now, in a random sample of 500 young men between ages 18 and 20, that's supposed to be for 8th and 4th and 12th grader though, okay? But then they randomly select 500 young men in much older ages. They found that the mean NAEP math score is 272. Now, do we have evidence to support the claim that young men nationwide have mean score below 275? So after this long paragraph, just to find the claim, you need to dig in. You need to read the whole question first though. Then you need to dig in and you see, do we have enough evidence to support the claim that young men nationwide has a mean score below 275? So after you read that one long paragraph, the first step is to find what's the claim. Okay. Now I wonder if you ever watched, is it C-SPAN? Like when the Congress or Senate has the debate, right? And a senator or a congressperson asks question to a witness. Sometimes the question has a very long introductory paragraph, maybe more than one paragraph, okay? And the question is very short. Now, so that sounds more like giving a statement, giving a speech than asking question to witness. So they set it up in a way that the witness has no way to answer the question in the right way, because whatever you say, either yes or no, it will be wrong. Okay, now then the thing is, good thing we are not in that kind of setting, but more or less you need to read the whole problem, and the whole paragraph, and the first thing you need to do is to find what is the claim to start with. Okay. Now, the claim may be buried in between. The claim in this case is young men nationwide have a mean score below 275. Okay, and then step 2, hypothesis. Null hypothesis, alternate hypothesis. The mean is below 275, have no equal sign, so it goes to the alternate hypothesis. The complementary statement will be the mean is at least 275. Okay, now I have 1 minute left, so instead of going to question 2, you can continue from here. Okay, I have question 2, and then we start with step 3. Okay, and then on Monday I will go on with step 3. Okay, so you can try this question 2 and question 3. Okay, but what is the main purpose of hypothesis testing? Okay, let's take a look in the following situation. They say that 275 is the cutoff score. Okay, now the thing is, with the sample size of 500, we have the sample mean of 272. Now, of course, the sample mean is clearly less than 275. Okay, but the problem is does it mean the mu is less than 275? Okay. The sample mean is clearly less than, but does it mean the population mean, the overall, everybody ages 8 to 20, young men, the average NAEP math score is less than 275? Now, the thing is, do you consider, is it possible that you just happen to get a sample in which 272 is less than, in which the average is less than 275, just a little bit? Okay. Is 272, which is 3 points to 275, a small difference that may happen by chance because of sampling error? Now, how about the sample size of 500, which is actually very big? Okay. Now, I like this question because it makes you think. Is 3, so imagine if I change this question 275 to 72 into this situation. My coffee can here. I wonder if you see me. My coffee can here. Yeah, my coffee can here. Okay. Let's say it says underneath. Let's say it says underneath 275 milliliters. Okay, and then I pick 500 such cans and measure the volume of the coffee in there, and I found out the volume of the coffee in this 500 cans is 272 milliliters. Now, of course, nobody will say because of missing 3 milliliters, because of missing 3 milliliters difference, then somebody get really sick, not enough coffee. Nobody will do that, right? But for monetary purpose, in America, people sue everybody for very, we have more lawsuit that is unreasonable than reasonable ones. So in case you want to be part of that unreasonable one, just for the purpose of money, okay? Well, you know what? The company actually make a claim which they don't deliver. They say the average is supposed to be 275, but from 500 cans that I purchased, it's only 272. Okay, and can you file a lawsuit against that company? And do you have enough evidence to support your claim that the company actually cheating the customers? The sample mean 272 is clearly less, but does it mean all the cans on average has less than 275? Okay. Now you don't want the company to actually open all the cans and test and find out the average. Okay, they have nothing to sell if you do so, just for your lawsuit, right? Okay, but then before the jury, before the judge, you need to argue that yes, 272 may be just 3 milliliters less than what they claim. So it could be sampling error, but my sample size is so big such that that's actually considered very different. So I would like the company to change the claim on the can to be 272 instead of 275, and pay 3 cents back to everybody who had bought that coffee. You know, it actually takes more time and energy and money to pay that 3 cents to everybody, right? Okay, you call it what? Frivolous lawsuit, right? Okay, yeah, but that's what we are getting into. How much less is too less? Okay, simply because it's a little bit less doesn't mean it's really less. It is possible it's because of your sampling error. Okay, now I will stop here. I will continue on Monday, but if you have a chance, please read this handout. Don't forget to start studying for your test 3 though. Okay, see you then on Monday.